Good afternoon, everyone. Welcome to the Mariah Mitchell Association's Pop-Up Science Speaker Series, featuring two of our very own, very special post-baccalaureate research fellows, both Emmy Wisz and August Muller, who are also hosted by Dr. Regina Jorgensen of the MMA this evening. Welcome, everyone. How are you? We love the tandem tech. Before we get started this evening, I'd like to share a special thank you to our lead sponsor, Bank of America, who makes this program complimentary and accessible to all of our viewers in person as well as virtually. I'd also like to pay a special thank you to Cisco Brewers of Nantucket, as well as White Elephant Hotels and Resorts. If I did not introduce myself, I'm Janelle Gurley, Director of Science and Programs at Mariah Mitchell Association. And this evening, both Emmy and August will be presenting a featured presentation titled In a Galaxy Far, Far Away, Spectral Analyses of Distant Galaxies. A quick brief bio on Emmy, who obtained her BA in Astronomy and Physics from Bryn Mawr College. Her undergraduate research focused on galaxy formation and evolution, studying the impacts of morphology on radial metallicity gradients. She is excited to continue to be involved in the field of galaxy evolution, researching damped Lyman, gamma, DLA systems to expand on her understanding of the formation of galaxies over time. And Regina can tell me if I got that correct. And also this evening, August Muller, who holds her BS in physics from Haverford College. Her undergraduate thesis investigated techniques for detecting extreme mass ratio in spiral gravitational wave signals from the upcoming LISA gravitational wave detector. During her year on Nantucket, August is excited to learn more about observational astronomy as she investigates the host galaxies of fast radio bursts. Join me in welcoming both Emmy, August, as well as Regina this evening. Welcome to you all. And I will turn it over to Dr. Regina Jorgensen to also welcome our post-bac fellows this evening.
Thank you, Janelle, for that intro.
You are very welcome. And you can grab the screen whenever you are ready.
Okay, we will go ahead and share. Okay, can you see that okay?
Yes, I can.
Okay, great, okay. All right, hello everyone, and welcome both on Zoom and in the room. Thank you so much for taking the time to be here today. I am Dr. Regina Jorgensen, the Director of Astronomy here at the MMA, and I am really excited to introduce everyone to our two post-bac research fellows who are with us for this year, and have them talk a little bit about their research and basically how they're spending their time while they're here with us. But I thought to start off with, I wanted to talk just a little bit about what it is to do astronomy research, what we basically do all day and night with our time, and how that process kind of works, just in case people are not familiar with it. And so, oh, click on the slide, 1 second. Yes, click on this slide. All right, so I'm gonna use some very technical explanation. No, I'm just kidding. This is actually a cartoon, the comic that I drew, to sort of explain. I should say now this is from a very observational astronomy perspective, and there's actually lots of different kinds of astronomy. You can be a simulator, which means you work with computers. You could be a theorist, which means you mostly do equations, paper and pencil. And you can be an observer, which means you go out and use telescopes and look at the sky. So we're a little bit more observational biased here at Mariah Mitchell. So that's what we're going to be kind of focusing on. But all of those three different kinds of astronomers have to work together to really make progress. So there's a lot of collaboration amongst these different types. But so this is what many people think. We go look through the telescope, and then we sit and we analyze the data. This is a person scratching their head, if you can't figure out my stick figure. So we sit and we analyze the data at a computer usually, and then we have amazing science results and they're picked up in the news and everybody's excited, right? So that's kind of what I think the perception a lot of people have of how astronomy research or research in science goes. Unfortunately, that is absolutely not the case, okay? There are a lot of different parts that we can't encapsulate in that little cartoon I just showed. So this is a kind of visual representation of the scientific method. If you all remember back to middle school science, where you probably learned about the scientific method, this has some of those points. You know, you can start kind of anywhere here in this circle. For example, you make some observations, think of interesting questions like why does that pattern occur, formulate a hypothesis, why you think it's occurring, develop testable predictions. So what do you think might happen if this hypothesis is true? And then how, more importantly, how can you go test that? Gather data, refine, alter, expand, or reject, you know, and then develop general theories, make more observations. But what I want to point out here is that this little subcircle in here is actually where we spend most time, going around and around and around and around here before you can come out. Okay, and it actually takes quite a lot of time and quite a lot of work to do this cycle. And I think one of the best ways that I can explain this is maybe by telling a particular example from my own experience. Back in 2004, this is me. I was in graduate school and I was trying to figure out a dissertation topic for my PhD work. And so I had an idea of something that would be interesting to do. And so I wrote a proposal to go do that on the Keck telescopes. I'll just point out, when you do this process, it's very competitive. So there's, for every proposal that gets time on the telescope, there's about 6 to 10 other proposals that don't get time. So I ended up being really lucky and getting time on the telescope. And I went to Keck, because back in that day, the only way you could observe was to travel there. And unfortunately, it was cloudy. So I didn't get my night. And also, unfortunately, if you have time like that and you get clouded out, that's it, you just lose it. You don't get a makeup time or anything like that. So that's it. You have your assigned night or nights. If they're clouded out or whatever, it doesn't happen for any reason. You go home, you cry, and then actually what you do is you go back to work and you figure out, okay, how can I reapply? Do I have to change my targets? Do I need to change my proposal a little bit because new research has come out, altering things and whatnot? So you do some work. And then a year later, because the cycle is about a year, I applied again, you wait about a year until you can reobserve. Okay, so I went back. This time, it actually wasn't clouds, but what happened was there had been a snowstorm, and it was torturously clear and beautiful skies, but the snowstorm was so intense that it iced over the domes, and they couldn't open the domes because of the ice, and they couldn't get the ice off because these are really, really giant, large domes. And so we were sitting there under completely clear skies, and we couldn't observe. That was a major bummer. So we go back to the office. I, of course, try again because this proposal is really good, right? They keep giving me time, so they like it, but I keep getting weathered out because it's just terrible luck. So 1 year later, we got more time, go back to the telescope. This time, the volcano on Mauna Kea decided to erupt around that time. And this happens occasionally. And when it does, sometimes it can, there's ash and whatnot from the volcanic eruption. And they don't open the domes if that's the case, because they have to protect the telescopes and whatnot. And you can't see anything anyways, because the sky quality is really bad. So I got weathered out for volcanic eruption, go back to the office, another year later, get more time through these competitive proposals, right? And this time it was wind, actually. You don't often think of wind as being a problem, but if it's very windy, they also won't open the domes because it's dangerous, because these are like basically like giant sails, you know, and the wind comes in and whatnot. So I've had all and this is no future foretelling about the next week or so, because I've had all the bad luck already. So Meanwhile, I'm in graduate school and now years are passing. Of course, I don't just sit there twiddling my thumbs because I have to write a dissertation and get out of graduate school in a certain number of years. So, in the meantime, I'm doing lots of other things and I'm trying to figure out research that I can do to turn it into a dissertation. And I'll come back to that in a second, but the end of this story, this particular story, is a happy one. But it took about 10 years. So 10 years later, in 2014, was when I finally managed to get that first data that I was trying to get, and worked on it, wrote papers. And by the time that all came out, and we did get a lot of press for this actually, because it was studying baby galaxies in the early universe, which you're going to hear more about tonight. But so that took about 10 years to get from the beginning of an idea to a final product that you might see in like a press release if it's worthy science. And so just to go back to the comic, what happened was every time when you're not observing, you're actually thinking with lots of other people. You're, reading the literature that comes out, talking with people who are publishing other things that you need to consider for your work, meeting with collaborators all over the world. You're writing proposals, you're writing papers. There's this constant back and forth of things that are happening all the time. And all of that stuff takes actually quite a lot of time. So it's sort of like this, juggling, a bunch of plates at the same time. So hopefully that gives you a little taste of what it's like to be an astronomer and doing research. And, of course, along the way, we get a lot of support from wonderful organizations like the Maria Mitchell Association and the National Science Foundation. And so I'm going to transition now to introducing a little bit more fully August and Emmy. And I just wanted to throw up these two slides because both of them are working as part of two different collaborations that we have here at the Maria Mitchell Association that are funded in part by grants from the National Science Foundation. This is one of them called the Fast and Fortunate for FRB Follow-Up Collaboration, also known as F4, because there's 4 Fs there. And as you can see, this is actually not even a super complete list of our collaborators, but this is some of them. Our primary collaborators are at the University of California, Santa Cruz, of course, Maria Mitchell, Northwestern in Chile, and then a couple other institutes that I didn't even include on here. This is a pretty big collaboration at this point, and it is several years old. We started this back in 2019. So it's been running. Our first 3 postbacs that we had here at Maria Mitchell were all members of this collaboration. About 2 years ago, though, we were also given another NSF grant that allowed us to start a second collaboration that we call, wonder if I can get that thing to go away. Oops, shoot. Sorry for everyone on Zoom. We have a little thing on the screen that I'm just, it's not letting me, and it doesn't show up here. Okay, I'm going to continue. This is our second collaboration, which is called MANGOS, which is an acronym that stands for, sorry, this is a lot of words, multi-wavelength analysis of neutral gas observed in emission with spectroscopy. And we'll tell you a little bit more about what that means today. Our main collaborators here are at Space Telescope, Science Institute, of course, Maria Mitchell, Johns Hopkins University, at the ALMA Institute in Italy and in India. And so, as you can see, these are both somewhat big international collaborations. And I didn't give a credit here, but credit goes to August, who used her graphic design skills to actually design our logo for the MANGOS collaboration. There's a lot of detail in here. Just going to point out, if you look at the leaf of the mango, this is actually a science spectrum right here that contains the kinds of things that we're looking at. And this is science as well. This color is actually science. This is what we call the rotation curve of the galaxy. So it's a map of how this particular galaxy is actually spinning. So it looks pretty, but it's also science, which is always fun. So yes, we have our 2 post-bac fellows for this year, Emmy Wisz, who's a graduate of Bryn Mawr College, and August Muller, who is a graduate of Haverford College. And I'm just super excited to have you here. I mean, you've already done such amazing things. Both of them started in about mid-August of this last year, and so have been working with us for about 4 months now. And I think they'll mention this, but they're also going to be taking off soon to go to Keck actually to do some observing for both of their projects. So that's really exciting thing. Okay, I think they're going to each introduce their title of their talk and then of course tell you about their research. So we're just going to take a quick second to change the slides here. And if you want to come up, Emmy, do that and then share screen, right? There you go. I don't know how to get that little closed captioning thing to disappear.
I wonder if you go like here.
Janelle, I don't know if you can see that closed captioning thing. There's a little X, but we can't seem from our end to close that X.
I closed it for you. Is it gone on your end?
No, we still see it. Let me stop sharing. Yeah, where's the Zoom window?
I think you're in, I think.
Oh, it's right there. There you go. Okay, cool. Okay.
Is it sharing screen now? Janelle, can you see my slides? Yes, okay.
Yes.
All right, we can get started. So I'm Emmy. So I'm going to be talking about chemical enrichment of the universe over cosmic time. That's a lot of words, but I promise we'll get into all of what that means in a minute. I guess first I would like to re-acknowledge the NSF and the Environmental Association for funding. And then of course, August's freshly minted logo for mangoes, which is the collaboration that I'm a part of that is very supportive. So hello. So all those jargon words to say, the main question that we're going to try to answer in this presentation is how do we study the history of the universe? Again, another really big question, understandably. So we're going to break it down into a couple of parts. So first, we're going to look at galaxies, what they are, how they form and change over time. Galaxies are much like people in that they are born in some way and evolve over their lifetime. We'll then move into how metals are created in the universe, what a metal even is, what am I talking about when I say that, how the universe has become more chemically enriched over time with those metals, and then we'll talk about a metric called metallicity. And then finally, we'll talk about the baby galaxies, also known as damped Lyman-alpha systems, or DLAs for short. And we'll talk about how those can be useful probes for cosmic evolution. Again, lots of jargon, but I promise we'll get into it. So to start, galaxies, we know them, we love them, we live in one. If you're unfamiliar, galaxies are massive gravitationally bound collections of stars, gas, and dust. They're very dynamically active. There's a lot of stuff going on in them. So here we have an image from NASA's JWST, the new premier space-based telescope. You probably have heard about it. And every single point of light you see in this image, aside from these ones with the spikes, is a galaxy. So just for some size reference, the size of this image is the equivalent if you took a small grain of sand and held it at arm's length up on the sky. The teeny tiny patch of sky that is covered by that grain of sand is the size of this image. So there's a lot of galaxies out there in the universe. Because of this, we're really interested in studying how they have been born, how they formed, and how they've evolved over time. I'll point out one interesting feature of this image. There are a lot that I'm happy to talk about later if people are interested, but this main bright cluster in the center, these more white-looking galaxies, this is a cluster that is 4.6 billion light years away. What I mean by that is the light has taken 4.6 billion years to travel to us. So light travels at a finite speed. It's very, very fast at about 300 million meters per second, but it is a finite speed. And because of that, it takes the light time to travel through space towards us. So in astronomy, when we look deeper into space, we're actually looking into the past of the universe. So this galaxy cluster in the center, for example, we're looking at it as it was when the light was emitted and traveled to us 4.6 billion years ago. So that's a little bit about how we can understand how galaxies have evolved. One way is just by looking at them simply by looking at them through images. So if we start with the Milky Way galaxy, this is our home. This is an artist representation, and from this you can see that there's a lot of data and information encoded in this image. All of the art in this photo is based on real data that we have about the Milky Way, about positions of stars and gas clouds and things like that. So we know a lot about the Milky Way just because we live in it. If we take one step out into space, we reach the Andromeda Galaxy. This is our nearest large neighbor galaxy. And again, we know a lot of information about her. She's often used as a reference for the Milky Way galaxy just because it's so close to us. So we will look at the Andromeda to try to understand larger scale structures that we can't see from inside our own galaxy. If we take one further step out into space, this is still within our local group or the local neighborhood of our universe. This is the Triangulum Galaxy. Again, lots of information in this picture. It's very detailed. We know a lot about it. And the reason why it looks a little different is just because it's a different type of galaxy, but there's still just as much information that we know about this. However, if we take a large step out into space, we reach galaxies that look something like these. You can clearly see that there's just not as much detail as we're able to pick up. You can see some structure maybe in this one, but they turn a little smudgy, a little faint. And then if we take an even larger step out into space, we reach galaxies that look like this. They're smudges, I'll be honest. There's not much going on there. There's a lot going on there, but it's hard to understand and see what is happening there. So clearly, as we move further out into space and look further away, closer to the beginning of our universe, it's hard to understand what's happening in these really faint galaxies because we can't pick up as much information from them. So instead of looking at galaxies through images, there are other ways in which we can study this formation. The method that I'm most invested in is looking at the metal enrichment of galaxies. And I'll talk about what metals are in a second. So in astronomy, metals are really anything heavier than hydrogen and helium. So hydrogen and helium, we probably all know, are the lightest elements on the periodic table. In astronomy, we refer to literally anything else as a metal. And the measure of these abundances we call metallicity. So that's great and all, but how are metals actually formed in the universe? To understand this, we go back to stars. So this is a process called stellar nucleosynthesis that all stars in the universe undergo. It is the process of fusion at the core of stars. So stars have a lot of energy they want to use up as they live their life. They'll start with hydrogen, the lightest element, and they'll fuse all of those hydrogen elements into helium elements, and they'll keep doing this until they run out of hydrogen atoms, and then they'll move on from hydrogen to helium, fuse their helium atoms into carbon, and so on until they run out of energy. The maximum step for this process is iron, and this is because the process of iron fusion into cobalt takes a lot more energy to conduct than it produces. So what happens if a star reaches this point? So if we start with a star that's much like our sun, a very average star, it's going through this process, it's living its life. It might reach iron, it might not, depending on how much energy it has. But once it reaches that point, it will try to expand because there's an imbalance in pressure from this process happening in the center and the inward pressure of gravity trying to keep the star in its shape. So the star will expand to try to compensate for this pressure imbalance, but this is a very unstable phase in its life. They don't really sit here for very long. But what will happen next is that the star will explode and send all of those metals that it's created into the space around it, the interstellar medium. What's left from this process is what we call a white dwarf, which is the dead core of the star. However, what's important about this process to understand is that these metals are A, formed in stars, and B, recycled through galaxies, as each consecutive generation of stars is able to start from a more metal-rich cloud of gas and dust. This turns into an elemental abundance that we can actually measure in the universe. So we can see here that we got mostly hydrogen and helium. These were two elements that were formed just after the Big Bang, but all of the other elements in this particular figure are elements that we looked at that were created in the center of stars. But why do we even care about elements at all? What does it matter to us here on Earth how elements were formed in the universe? So humans are actually made of elements. To drive this point home, we have a little pop quiz. So what do we think is the most abundant element in humans? Anybody have a guess? Carbon? Great. It's actually hydrogen. I learned this too the other day. But what's important to know about this is that all of these elements that we see here were elements that were formed in the the stellar nucleosynthesis that we looked at earlier. So if you've ever heard anyone say that humans are made of star stuff, this is exactly why. So if you walk away with nothing else, now you have a fun fact about that we're made of stars. So now that we understand metallicity and how we can measure it and why it is useful to understand how galaxies have evolved over time, we're going to go back to talking about that we're trying to create this timeline of how metallicity has evolved over time from the early universe up until now. So if we remember earlier, those really faint galaxies we looked at, it's hard to get information from them. Here are some more recent science images from some of the farthest away, faintest galaxies that we've been able to study in the past couple of years. Again, just to drive home, all of the points of light you see on this screen, except for these ones with the spikes, are galaxies. And then some people have very nicely popped out the faint ones. But again, we arrive at this problem that faraway galaxies are really, really faint. So it's really great and all that we can study galaxies close by. But if we want to create this timeline of understanding how the metallicity has increased over time in the universe, we need to study these faraway faint galaxies. So because they're so far away and so faint frequently to be observed directly, we must find some other way to observe them. This is where damped Lyman-alpha systems come in. I'll probably refer to them as DLAs for the rest because it's kind of a mouthful. But we will get into how they can be useful probes for this cosmic metal enrichment over time. But first, how do we actually get data from looking at galaxies? We use a process called spectral analysis, where we take the light that we receive from these galaxies and we split it into the component parts called a spectrum through a prism. So if we want to do this kind of analysis on a continuous light source, like a burning star, for example, or a lighthouse, these are emitting light at all wavelengths. So if we do the spectral analysis, we get a spectrum here, this color bar, where you can see that there is color at all wavelengths of light. The bluer and more purple colors correspond to shorter wavelengths, and the red colors correspond to longer wavelengths. We can then take a spectrum like this and turn it into a science graph where we have wavelength on the x-axis, and brightness on the y-axis. If instead of studying a continuous light source, if we want to study a cloud of gas that is glowing, emitting light, what's happening with the elements in this cloud of gas is that they are emitting photons of light at particular wavelengths. So instead of getting a continuous spectrum, we get what we call an emission spectrum, where there are bright patches at very particular locations. All elements have a fingerprint of emission spectrum, where we can look at these bright features and their locations and understand exactly what elements are contained within that cloud of gas. Conversely, if we look at light that has come from a continuous light source and traveled through a cloud of gas on its way to us, the elements in the gas cloud do the opposite. They absorb photons of light at those particular wavelengths. And instead of getting these emission features, we get absorption features. Where in the same way, but instead of bright patches, we get these dark patches at very particular locations. And we can understand exactly what elements were in that cloud of gas that the light has passed through. This is exactly the geometry of a DLA. So a DLA, which I've been skirting around, is just a really, really dense cloud of hydrogen gas. We call them baby galaxies because this is what the first galaxies were formed out of. They had to start somewhere, and this is where we think they started. So instead of using a lighthouse or a star, for example, to illuminate this galaxy that would otherwise be invisible to us, we use what we call a quasar as our bright background source. Quasars are actively accreting supermassive black holes at the center of galaxies. Because of this, they are extremely luminous. They are one of the most luminous things in the universe. And because of this, we can see them at very, very far away distances, which becomes crucial to this method of observing DLAs. So if the light comes from the quasar and passes through the DLA on its way to Earth, we get those absorption features that we just looked at. And from those, we can understand what metals are within our DLA, and therefore what metals are within these baby galaxies. So I'm now going to show you a real spectrum of a DLA and of a quasar setup. So again, we still have wavelength on the x-axis and brightness on the y-axis. If we have our quasar here, again, like I said, they're extremely luminous, so we can see them at especially far distances. Because they're so bright, they cause these really bright emission features. And then as the light travels from the quasar to us on Earth, and it interacts with this cloud of intervening gas, or our DLA, that gas will absorb a lot of those photons of light at a particular wavelength and cause this really extreme absorption feature, this really big trough here. And from a spectrum like these, we are able to get metallicity information. We're able to measure what metals are within that cloud of gas. So To do measurements like this, the Mangos collaboration uses a series of world-class telescopes. The one that I will highlight here is this big picture here. This is Keck. This is where August and I will be traveling later this week and next week. Hopefully we have better luck than Regina had during her PhD. But it's really great to have these collaborations to do really amazing research. So now that we know about metallicity and metals and what DLAs are and how we can use them to study the universe, what do I actually do here? So I have been doing exactly what I've been talking about. I've been making a timeline of DLA metallicity over the history of the universe. So we have time on the x-axis, we have present day over to the left, and then the Big Bang all the way off in this direction. And frequently in astronomy, we will take measurements of things that we can and compare them back to our sun. It's the closest big thing we have to us. It's a very consistent source of data. So on the y-axis, we have metallicity in reference to solar, where solar is metallicity that is equivalent to that of our sun, and then increments downward. So all of these points here are DLAs that have been measured. Each one of these points encodes a ton of research. The whole process that Regina talked about earlier, that's all happened for each one of these points. So all of the blue points on here are work from previous people, previous Mango collaborators, other international collaborators that also study DLAs. All of these red points are DLAs that I've been intimately focused on as my work here at MMA. But this is a lot of information to look at once. So one way in which that we can analyze something like this in astronomy is by creating binned averages. So if we do something like that, we get this, where we have all of our bins and then the average metallicity in each bin. Still kind of a bit to look at. So the next step that we would take is to fit a linear trend to this, just a straight line fit. And that looks like this. You might notice something a little off about this. That would be that my pink point over here does not really fit on this line. This is specifically what my work's been focused on, is we are trying to understand if this trend turns over at any time. What I mean by that is if we let this trend continue off towards the Big Bang, does it continue on this path or does it fall off at some point? What's hard about understanding this is that DLAs in this regime, which is where I've been studying them, it's one of the hardest distance regimes to get information from. Even though we have these really bright light sources called quasars, they still become a little bit faint at this point, and there are not as many of them that we can find. So I've been spending a lot of time with all of these red dots, these ones out here specifically, trying to figure out what is happening at this trend at this distance regime, which has been really fun so far. So in short, we looked at how DLAs can be probes for cosmic evolution by using their metallicity values to create a timeline. We started with galaxies, how they're dynamical systems, much like people that are born in some way and evolve over their life cycle. We looked at stellar deaths and how they enrich galaxies by creating metals and then recycling them through galaxies. And we looked at DLAs and how they are useful probes. They're a special tool we can use to study galaxies that we would not otherwise be able to see directly. And then we finally looked at cosmic metallicity and how it has been increasing over time. However, we're trying to explore this highest distance regime, which is one of the hardest regimes to study, to figure out if the trend continues. I would again like to thank Mariah Mitchell Association specifically for funding and support, and I can now take any questions. Yeah.
Very nice job.
Thank you.
Very nice job. So,
Anyone in the virtual sphere has any questions, please type it into the Q&A box, and I'm happy to moderate and share with Emmy.
one of the questions I have is, in terms of the work that you've been doing, what percentage of the work is done via like crunching data that you're getting from another remote telescope that's observing versus a telescope that you might actually be looking through? And is Keck when you go to Keck, like, is the point of the trip, is this like the first time maybe you will get to see this up close and personal, right? Like, because you've been doing all this work.
Yeah.
But because I also had the privilege of interviewing you.
Yeah.
So I got to ask and understand some of this. But I'm wondering about, like, is that what, so because it seems to me like you're at a seminal moment here.
Yeah, I definitely am. That's a really great question. I thank you. So it's kind of a mix of everything.
The question.
Can you guys hear the question on Zoom?
If you would repeat it, that would be great.
Yes. Okay. Joanna.
Yes, I won't repeat it. You'll repeat it because they can't hear me.
Yeah. Joanna is asking me how much of my time is spent crunching numbers that I've gotten from a telescope like Keck, and if Keck is kind of a big experience for me coming up in this research. So I think to answer that, I spent a lot of time crunching this. So the data that I've been working with explicitly, so all of these red points kind of in that side, and some of, I think maybe one of these are DLAs from a very intensive literature search that I've done. So I've been spending lots of time really digging into what has been published in the last 10 years to see what other people have studied. And then these 4 down here are ones that the Mangos collaboration through Dr. Jorgensen have collected in the past couple years. So that is data that was taken, I believe, at Keck. Correct me if I'm wrong.
Yeah, it's a combo of
Yeah.
SBLT, so similar type of telescope that's in the southern hemisphere and run by Chile. So there's a bit of a mix of different things here.
Yeah.
And do you think that you'll be able to prove or disprove the pink?
Oh, I think in this timeline, probably not. This is, like I've mentioned, this is a really, really hard regime to look in. It's just, there's a lot of different factors. But it just is really challenging, really like tedious work to take measurements of DLAs at this regime.
But that is the goal.
But that is the goal. We'll see how far I get. I think also what's important to know is that research is ever changing. People will be publishing. Once I publish this, someone probably will publish something similar right after me. And so you have to continually be updating what you understand and these kind of trends with newer data. Especially with the advent of the next generation of big telescopes, we can get more precise data.
We have a question from John Briggs.
Okay.
If I remember right, you use the term damped Lyman-alpha forests. Can you explain why you use that word? I recall a bit about the forest already.
Yes, I can do my best. What would be the best thing to get to? Okay. So it's called damped Lyman-alpha because, I don't know if you can't see me point. This is crucial. I'm sorry. So this is a Lyman-alpha emission peak, which is a hydrogen transition that happens. As the light moves from the quasar through space to us, a lot of that hydrogen emission gets absorbed by the gas. So a lot of this is what you're referring to as the forest. It looks like, we call it a forest because it looks like a little forest of trees. But these are all absorption features that are very similar to this one. They're just not as strong because even though our galaxy, our DLA, is a really massive reservoir of hydrogen gas, there's also hydrogen gas just out in space. So a lot of, well, not just out in space, but for now. So all of this is what we call damping of Lyman-alpha. As the light comes from the quasar and moves through space to us, it gets damped, so it's much shorter. And then we get our DLA trough here. So that's where the damped comes from, in short. Yes, Jack.
Okay. So I'm curious about I guess part of the process here. So you need a quasar that goes through a DLA to analyze it. So I guess how do you find those circumstances in a field of a gazillion points of light? Like, you find a quasar and hope there's a DLA in front of it, or find a DLA and hope there's a quasar behind it, or it's like AI now looking at all kinds of light, like finding those scenarios that you can analyze, or how does
That's a great
work?
question. Jack is asking how we discover DLAs. Like, what's the setup there?
Do you want me to take it, or are you
I can give it a go.
Okay, slow.
Slow. Okay, so
Sky survey.
yeah, so there are a lot of surveys of galaxies out there. One of the biggest one is the Sloan Digital Sky Survey, which is just a really massive survey. But it encodes information. So someone's done a lot of reduction of that data. Someone's analyzed all those different galaxies. They go, this is a galaxy, this is a star, this is a quasar, whatever. You can take the data from such surveys like that, and you can pull out all of the quasars, and then you can look at this. So all of those objects that the surveys looked at have a spectrum. Something like this, maybe not quite as intense, maybe quite as intense, depends. And what you do is you pick out the ones that say that they're a quasar, they're flagged as a quasar by the reduction analysis process or somebody that's looked at it themselves. And you can see in the spectrum that there's a DLA. And then often what happens is people will go follow up and say, oh, well, there's supposed to be a DLA here. We know that there's a quasar in the line of sight. And then you can study the DLA in more depth that way. it's hard to like hunt for DLAs because you can't just like point a telescope somewhere and discover them. The point is that they're so hard to see directly, and you have to have this this really bright background source to kind of illuminate something that we otherwise cannot see directly. Some people discover them like serendipitously, like they'll be studying a quasar survey, like they'll be doing their own quasar survey and they'll find some DLAs along the way. They're quite common, especially in the closer universe. I think about 1 in every 3 quasars is supposed to have a DLA.
Yes.
Yeah.
Yeah, and the other point here is these initial surveys, like the Sloan Digitized Sky Survey, they looked at almost the entire sky, took spectra of millions of galaxies and quasars. So we have this giant sample at low resolution though, so it's low spectral resolution. So if you see a DLA, because that feature is really big, you can even see it in low resolution spectroscopy, you can see this feature. And then you go back with a high resolution spectrograph like they have on Keck, which this is, and you can then get a lot of the detail here that you don't get in the low resolution survey because it's very expensive time-wise to do that.
But really,
So-
But yeah, basically 1 DLA per 3 quasars. So they're everywhere on the sky,
Yeah.
basically.
well, and there's some quasars that have multiple DLAs in the line of sight. So you'll get a couple of these troughs in to the left. I mean, those ones are extra fun to look at. That's actually the first part of my observing in Keck is looking at some quasars that have 2 or 3 DLAs in between the quasar and us. And you just know that because you get a couple, like more than one of those features.
You can see there's another system here. This is not quite strong enough to be a DLA, but this is another, it's like a sub DLA. So it's not quite what we call officially a DLA, which there's a specific cutoff. And this is just below that, but you can see how there's another feature here.
Thank you, Emmy and Regina. 2 comments, rather 1 comment, 1 question at home. So Celia said, no question, but I wanted to thank you for your excellent talk. Your explanation of emission and absorption lines in Spectral was great, and I'd like to echo that.
Thank you, Celia.
And Kate says, since we rely on quasars to light up what we are trying to see, is part of the reason it is harder to figure out metallicity as we get closer to the Big Bang is because they are faint, or is it because they're hard to see?
Both, actually, that's a good question. So the quasars do become fainter. There is a limit as to how much light we can receive from something. Also, once you get, oh, this might be a lot. Where is it? Okay. There's a lot of information on the slide, but this is like in short the history of the universe. So over here we have present day. So these are like really defined galaxies. And then we're looking back towards here. This is kind of where we can see some of the furthest DLAs. But there is kind of a limit to which we can see bright objects or to which things have formed. So at some point, there is a cap on where quasars have first formed. So that's one reason why it becomes very hard to find them at such far distance regimes. A, because there are not as many, and B, because they become much fainter themselves. Even the bright background source becomes a little bit fainter and harder to see.
Thank you, Emmy. Question for you. Can any supporting observation be done here from Nantucket at our observatories, or does this largely rely on larger telescopes?
Oh, I wish that would be so cool, but I guess like the whole thing is that they're so faint that they can hardly be, like they can't be seen optically or with telescopes directly. Unfortunately, we do need really, really high resolution telescopes to observe the quasar and observe the DLA in the quasar spectrum. Yeah, you just need really big telescopes.
That's fair. And the chemist in me is very, what's the word? Not concerned, but curious as to why is it that everything that's heavier than hydrogen and helium in astronomy, why do you consider them all to be metals?
Astronomers are notorious for really bad nomenclature and bad naming. And, I think it's a historical thing because astronomy's kind of been around forever. So, and people just decide something and then everybody kind of keeps that naming instead of reading about it. So apologies to any chemists.
My silent answer is that hydrogen and helium were formed just after the Big Bang.
Mhm.
And everything else was formed within this process of stellar nucleosynthesis and recycled in galaxies. Or things that are heavier than iron were formed in the earth or in other processes that are not within stars. And so I think that's like maybe the science answer as to why everything heavier than hydrogen and helium is a metal, just because of that distinction of how they were formed in the universe.
Okay. And what are you most excited about your trip to rather, but I'm eating my words tonight. What about Keck and this upcoming trip? What are you most excited to learn? What are you most excited to hopefully observe? How do you feel?
I'm super excited. This to me is like the original way of doing astronomy, right? Like Regina was saying, it's very uncommon now to get to travel to telescopes to do observing. So I think especially for someone like me who's a young scientist in the field, as this is becoming less common method of observing, it's a really unique experience to still get to partake in that while it's, you know, still a possibility. Plus I think like I've only met my collaboration on Zoom other than Regina so far, and they're all really amazing people, so I'm excited to meet some of them in person and interact with the Keck telescope people that are also, I've heard, really amazing group of people.
Awesome. Well, we're excited to hear about all that you learn on your trip. Thank you so much, Emmy.
Thank you.
Okay. We're going to do a little switch of slides here. Oops. Wait, I need to stop sharing and play.
And while we wait for the transition, Dan Bursch says, applause, applause.
Thanks, Sam. Echoing. All right. So hi, everyone. Just one more time, I'd like to echo the support from the Maria Mitchell Association, as well as the National Science Foundation, in really supporting me and all of the work that we do here in science. So with that, I'm going to start talking about the host galaxies of fast radio burst signals. I'll get into the definition of all that in a second, but let's first start. Let's first start with a little bit of overview of how this talk is sort of going to run. So I'm going to start with a little bit of background about how we do observational astronomy, all of the different types of light that I'll be talking about, because it kind of spans a wide range, actually. And then I'll get into what exactly fast radio bursts are and what their signals kind of encode scientifically. From there, I'm going to go into the science that I'm actually doing here at the Maria Mitchell Association with my rank of global collaborators, and specifically into the science of fast radio burst host galaxies. From there, we'll talk about some progress that our collaboration has made in the field so far, why this is really important, and finally go into a bit of our future plans and also some unanswered questions in the field. So we're going to start out with a little bit of a light crash course. By this, I mean this type of light. So all of the colors that you can see here, the rainbow of the prism, are probably all the colors of light that you think of when I say light, right? This is kind of our full spectrum. But indeed, there are a lot of different types of light that we as human beings can't actually see. And we call that the electromagnetic spectrum. So there are many, many, many different wavelengths of light, actually. It's not just limited to this small rainbow region in the center, though that's the only part of the electromagnetic spectrum that we as humans can see. And just to point out a little bit of kind of the physics of how this works is all waves of light travel at the exact same speed, the speed of light, as Emmy was saying, but the properties of the waves change. So going there all the way on the long wavelength side, we can have waveforms where a single light wave takes about a meter to pass from peak to trough. And then we can go all the way over here to the super short wavelength side, where these peaks are very, very close together. And another thing that I kind of want to just draw your attention to here is that because these waves, no matter what, are always traveling at the same speed, as the wavelength gets shorter, the frequency gets higher. This is like a direct proportionality. So you notice the peaks are a lot closer over here and a lot further over there. And that's true in time as well. So to go through a little bit of the electromagnetic spectrum itself, I'll start here in the middle with the optical wavelengths of light, which is what we're all very familiar with, right? That's our full rainbow of colors. But if we go a little bit off onto the blue side, and just for some astronomy shorthand, anything that's going towards the shorter wavelength side, we call bluer. Anything that's toward the longer wavelength side, we call redder. So you might hear me saying that throughout this talk. So slightly bluer of our optical wavelengths, first is ultraviolet light. There's a lot of ultraviolet light that's produced from our sun, and this is actually the type of light that gives us sunburns. Then, of course, we go into the X-ray regime, which is the type of light we use to take pictures of broken bones. And finally, all the way up to the very high energy regime, where frequencies are very, very high, are gamma rays, which is generally produced by some type of radioactive decay. Going now to the other side of the spectrum, just on the red end of our optical light is the infrared. Infrared carries information about the temperature of an object, actually. So if you've ever seen a thermal camera, this is actually using infrared light to do that. And finally, we get into micro and radio waves. And now, while radio waves are often thought of as a type of sound because of maybe your car radio, it's actually itself a type of light. So common misconception, absolutely no harm, no foul if you thought otherwise. But basically how this works is that our technology actually produces light waves where there are wiggles on the waveform. And these wiggles encode digital information about the song that's going to be played in your radio, about the text message you just received in your cell phone, maybe an email sending through your Wi-Fi router. So we use radio a ton in our daily life. It's really very helpful. And all of these are kind of something that we actually use even if we don't know it to be light. But also, these can all tell us very different things about astronomy and about our universe. So observing the exact same target in different wavelengths of light allows us to learn a very wide array of different things. And so to kind of explain this, let's look at our largest planet, Jupiter. So I'm going to start at the lower left in the visible, kind of starting in the center of the wavelength regime again. And you've probably all seen this picture of Jupiter or one very similar before, right? It has these atmospheric bands, these stripes across it. It has the great red spot that's been raging for years and years, a giant storm. And you might have seen a slightly lower quality of this through our Clark telescope at the Maria Mitchell Observatory here on Nantucket. So while that picture is beautiful and it does tell us a lot about the atmosphere of Jupiter and stuff like that, it's definitely not able to tell us the whole story. So going here to the X-ray on the high energy end of the spectrum, you see these bright pink splotches in the north and south poles of the planet. And these are actually aurorae, just like our northern and southern lights, but on Jupiter. Looking into the infrared again, as I explained earlier, allows us to gain information about the temperature of the upper atmosphere of the planet. And observing Jupiter in radio allows us to gain information about the magnetic field surrounding the giant planet. So now we have a whole suite of telescopes that are designed to search the heavens in all of these different kind of wavelengths of light. And once we started doing a whole lot of radio observing, we started to find these really strange signals called fast radio bursts. Oftentimes, these are abbreviated into FRBs for short. I'll kind of use these terms interchangeably throughout my talk. And fast radio bursts, when they were first discovered, were really crazy. They're super fast, they're super energetic, and we had no idea where they came from. The first one was discovered in 2006, and in the past 20 or so years, not quite, that we've been searching for these things, we've slowly been amassing information about them, but they really are still a giant mystery. And so fast radio bursts, I'm going to break down that title a bit, just about how fast. They're about 100 times faster than the blink of an eye. So 100 times faster than this, if you all caught that. I'll run it back in case you didn't see it. You'll see a little flash up there. 100 times shorter than that. So these are really brief signals. And in that tiny, tiny fraction of time, they contain about 1 billion times the energy that our sun puts out over the same amount of time. So incredibly energetic and incredibly brief. And what's more, these signals generally come from outside of our Milky Way galaxy, almost always, in fact. So the third kind of major surprise about fast radio bursts is that they've traveled quite a large distance to reach us here on Earth. So this is a bit of a physical setup, very similar to maybe what you saw in Emmy's talk earlier, where we have our own Milky Way galaxy, again, the same artist's rendition here on the right side. All the way over on the far left is what I call the fast radio burst host galaxy. This is the official term for the galaxy that these fast radio bursts have originated from. So an FRB host is basically the home of the fast radio burst source. And of course, every fast radio burst, in theory, we think probably comes from a host galaxy somewhere in the universe. In between is some intervening material. Here I've represented it as an elliptical galaxy, but this really could be anything. Clouds of gas and dust in the universe, whatever the FRB passes through. And importantly, when a fast radio burst passes through all this material, it is not entirely unaffected. So the main effect that we see in FRB signals is called signal dispersion. How this works is that some of the waves, in fact, all of the fast radio burst waves, the radio waves, are slowed down a little bit as they pass through material. This isn't incredibly surprising, right? Think things get kind of bogged down, right? What's kind of interesting about this dispersion is that it doesn't happen equally for all the different wavelengths of light. So the redder wavelengths, these are all in radio, but remember redder, longer wavelengths, get bogged down or slowed down a bit more than their bluer counterparts do, which means that we kind of get our signals spread out in time, where the bluer wavelengths arrive to our telescopes first and the redder wavelengths arrive slightly later. So I have a brief animation to show this. We have the FRB produced, and it splits out by color as it passes through the dispersing material. I'll play that one more time, just so everyone doesn't miss it. Here's our FRB, and here's the dispersed signal once it's passed through some intervening material. So what does that actually look like in our telescopes, right? Here's some actual data. So if we were right next to the fast radio burst host, there is no opportunity for dispersion. We'd see something like that plot on the left. On the x-axis down here is time. So say we start observing on the left of the plot and draw in our data towards the right. And on the y-axis is frequency. Remember, this is inversely proportional to the wavelength. So our bluer frequencies will be up here at the top and our redder ones down at the bottom. So our fast radio bursts at the source, all of the frequencies are produced at the exact same time. This is this vertical yellow line that you're seeing in this plot. But by the time the signal gets to Earth, it doesn't look like that at all. It actually looks like this instead. It has this sweeping kind of shape where redder frequencies down at the bottom arrive substantially later than smaller frequencies do. And so this is something we call the sad trombone effect because of the kind of shape of the drawing. And if you don't really know what I mean, this is the kind of wow sound effect that you've maybe heard before. So what exactly do we do with this science, since we've now discovered actually quite a large number of these signals? So I'm part of, as Regina mentioned, the Fast and Fortunate for FRB follow-up collaboration, hereby I'm going to call it F4. And this collaboration seeks to investigate these host galaxies. So we are by and large not a group of radio astronomers. We're very gracious to all the radio astronomers who actually find the FRBs for us. Our primary job is actually to find the host galaxies that we think that these FRBs come from. And we do this through a process called localization. And in order to do that, we use a number of world-class telescopes. Here are some examples of those. These are located both here on Earth as well as up in space. Some notable examples are, of course, NASA's Hubble Space Telescope. We proposed time on NASA's JWST. And then, of course, down here in the lower left are the two WM Keck observatory domes that Emmy and I will be observing on actually in just like a week. So that's going to be very exciting, and we actually will be collecting data for the F4 collaboration in like direct help of this very work. So what do I actually mean by localization? Basically, how radio telescopes develop a localization is that when they discover the fast radio burst, they can give us some idea, basically a little circle on the sky of where they think the fast radio burst came from. And that's these ellipses, the white dashed lines. So here's some really beautiful results of this, where fast radio bursts were localized to the spiral arms of nearby galaxies. So this work was done by Alex Mannings, who's a current graduate student at the University of California, Santa Cruz, and a former MMA RU intern, actually. So very close to home. Her work finding that all of these FRBs in her sample were localizable to spiral arms was actually very big news. Kind of made it around the globe. My personal favorite headline is this one from the Sci-Fi Channel here. A little bit silly. So anyway, it's really kind of, it got picked up in the press and it's got some really fun response too. However, localization is not always this beautiful. These are some really incredible examples here. So let's talk about like kind of the broader problem of localization, especially as we're looking at galaxies further and further away. So this is an image in a very similar scale to that which you saw in Emmy's presentation earlier. To steal her example, if you were to pick up a grain of sand, a single grain, and hold it up to the sky, right, at arm's length, the tiny, tiny patch that grain of sand covers is blown up to take this to fill this entire image. Now, these items that all have these kind of weird blobs in the center, these are foreground stars that have been masked out. They're actually why you're seeing dark spots in the center, is that these stars are too bright for the camera that's taking this picture because we want to detect these really faint galaxies. And so we've actually basically just like removed the data covering those foreground stars. However, every other dot in this image is a faraway galaxy. Not in particularly high resolution. This is one of those survey images like Regina was talking about in the Q&A earlier, and Emmy. But here's the thing. When we first started discovering FRBs, our localizations on the sky looked something like this. How are you ever going to figure out the host galaxy of your FRB, right? You can't. There are hundreds of galaxies within that localization. We really can't do a lot to determine where exactly the FRB came from. So this is a bit of a problem, and radio telescopes have come up with some incredibly clever ways to improve upon this for us. So let's zoom in a little bit. Here we're in the center, so just a fraction of that grain of sand now. There's still a good number of galaxies in the field, but to really represent what's exciting about where localization has been able to get to now at this distance, an FRB was detected on July 17, 2022, and the localization ellipse actually looks like this. Only one galaxy in there, right? This is ideal. This is what we like to see. This is a good localization. And so this particular galaxy, several billion light years away, is actually one of my current subjects of study here at the Mariah Mitchell Association. I'm doing some analysis of kind of properties of this galaxy and what it can tell us about FRB science. And I will actually be presenting on some results of this particular case study at the American Astronomical Society meeting in January, about a month from now. So what science can we actually do with this, right? And where have we gone so far? I argue that we can use it to discover the invisible in a little bit of a different way than what Emmy was talking about earlier. So before I can explain exactly what I mean by this, I'm going to give a little bit of a background motivating the problem of the missing baryons. This has been kind of one of the major problems in astrophysics for the past number of years. And to kind of break this down into a more understandable way, baryons are protons and neutrons. They're all of the elements in the periodic table. You and I are made of baryons, our whole world is. Basically, if you can think of something that's made up of atoms, it's made up of baryons. Everything we can see is baryons. So, despite the fact that it seems that there's a whole lot of atoms here on Earth, much less out in space in an image like this, right? This is, again, hundreds of galaxies in a single frame. If we sum up all of the baryons that we think we can see here in our solar system, on our Earth, in our entire universe, we get less than half of the number of baryons that theory says we're supposed to have. We're missing a lot of matter. And so what we are trying to do with fast radiobursts is to actually detect that missing matter that we can't see, right? And so for a little bit of how this process works, let's go back to that dispersion measure I was describing earlier. So if we take the dispersion that was caused by the gas and dust in the galaxy, the FRB host galaxy, and subtract that off from how much dispersion we actually see, then we do the same thing for all the clouds of gas and dust in our own Milky Way galaxy, as well as any intervening clouds that we maybe can see. Maybe there's another galaxy kind of just off to the side that FRB is passing through. Then we kind of have an idea of how much dispersion we expect to see in our signal. And what we found, the F4 collaboration of just a short couple of years ago, is that consistently there's always more dispersion that we see in the signal than that summation process tells us that there should be. Which means that the fast radio bursts that we're detecting are passing through some sort of matter that we cannot see even with our best telescopes. And so this has allowed us to show that these fast radio bursts are likely passing through what we call the cosmic web, which is very large scale structure, strands of hot, diffuse gas and dust that are not visible to us at all. They are hidden matter in plain sight. It's just not bright enough for us to see. So to give a little bit of scale about what you're actually looking at, it looks maybe like a slime mold or something here. And in fact, that's kind of an interesting clue you can ask me about later. But so these kind of red or yellowish splotches on this image are galaxies or galaxy clusters, right? Those are the things that we actually can see more or less. But all of the purple filaments are just clouds, mostly of hydrogen or other materials, other baryons, that are so diffuse, so spread out in the vacuum of space that we cannot see them at all, no matter how good our telescopes are right now. So discovering this cosmic web, of course, as you might suppose, since we're answering such a big question of the missing baryons, also garnered a lot of press. This is a very exciting discovery and something that we're kind of trying to push the envelope on as a collaboration. So where are we going from here, right? This is an amazing discovery. How can we kind of progress from this? So in the future of FRB science, particularly in the F4 collaboration, one of the main things that we want to do is push this out to further and further distances. Basically, all of the FRB host galaxies that we've been able to detect are pretty nearby. They're pretty much in our local universe. They're way, way closer than the galaxies that Emmy was talking about in her presentation. And so here is an image from the Hubble Space Telescope that was captured just this year by F4 member Alexa Gordon of Northwestern University. This is showing a galaxy group of 7 galaxies, rather far away. And the red ellipse here is our FRB localization. From this, we can conclude that our FRB most likely came from galaxy G1 here, where there are, remember, G1 through G7 in the group. And this is very exciting because, as it turns out, this galaxy group is more than twice as far away as the next furthest FRB host localization. So this is really pushing the envelope on how far into the universe we're able to detect FRB host galaxies. Now, I'm very privileged to have been able to help Alexa Gordon with this work and confirming the distance of this galaxy group. It's very exciting science. We submitted a paper on this to one of the premier astronomy and astrophysics journals just 2 weeks ago now, and are hoping to get a lot of press picking up on this in the coming months as this kind of hits the presses. So I've kind of been talking around a little bit of an elephant in the room. Some of you might have been wondering about this, which is what actually causes FRB signals, right? They're so crazy. You've told me where they come from. You haven't actually told me what makes them. And the answer is that's because we as science still don't know. So we have some ideas. And in fact, in the beginning, there were so many theories, including aliens. Spoiler alert, unfortunately, not that one. But we're still kind of trying to pin down this exact source. Now, luckily, a couple of years ago, we found a fast radio burst that originated from within our own Milky Way galaxy. And because it was from so nearby, it had a lot of information that allowed us to kind of narrow down theories. And basically what that source told us is that we're now thinking that FRBs are likely caused by magnetars. Magnetars, as my cartoon kind of indicates here, are dead remnants of giant stars. So to explain exactly what I mean, a magnetar is a type of neutron star, which is kind of the type of dead remnant after a giant star has died. The process by which that happens is a star much bigger than our sun, several times the mass, will run out of elements to fuse in its core. It will explode violently into a supernova, and then most of that mass, still several times the size of our sun, will collapse down into a very dense neutron star core, no larger than the size of a city. Now, these stars are very extreme environments. They spin incredibly rapidly, as fast as your kitchen blender. And in the case of magnetars, they have incredibly strong magnetic fields surrounding them. So these kind of crazy objects seem like a good candidate for producing fast radio bursts, right? They have these very extreme environments, much like we would think could produce these very energetic signals. But the truth of the matter is that we don't actually know how a magnetar could produce a signal like an FRB yet. And there are a lot of FRB properties that lead us to question whether magnetars can really tell the whole story. For example, some fast radio bursts, the majority of them, seem to be random one-off events, though there are several that are known to repeat rather sporadically. So one of the other things that we're doing as members of the F4 collaboration studying host galaxies is to see if we can find clues about what exactly might produce fast radio burst signals, in order to determine if the magnetar theory is correct and where exactly to go from here. To give a little bit of a summary, fast radio bursts are extremely bright radio signals that originate from outside our galaxy. These signals encode information about all the material that they travel through, and this information that's encoded has allowed us to discover hidden matter throughout the cosmic web. We're currently trying to study fast radio bursts from farther and farther away than ever before in order to map the cosmic web at farther distances and learn more about the history of our universe. And we are also trying to find clues about what might exactly cause FRBs and whether the magnetar theory is entirely correct. So with that,
thank you all for coming to my talk. Thank you to our supporters, and I can. Joanna in the room.
What, you know what, you may have said this, but I'm curious about this. What year did you first discover, or were these first discovered?
Yeah,
It's fairly recently, isn't it?
it is fairly recently. So the first FRB was discovered in 2006. And it kind of has picked up recently. So we didn't actually have very many FRBs at the beginning. More recently, we've gotten telescopes that are better suited to this, actually, radio telescopes. And so we are discovering more and more than we ever have. But at the beginning, even in the early 2000s, there really weren't very many examples.
And the one that you were working with the young woman from Northwestern, like what's the time frame that she recently saw that?
Yeah, so this FRB.
August.
Oh,
Well,
yes.
repeat the question,
Yes,
please.
sorry. First question was, when were FRBs discovered? That was 2006. Second question, or follow-up, I guess, is what is the timeline of this particular work from Alexa Gordon that I was working with her on? So this FRB was detected actually in June of 2022, so fairly recently. We got some ground-based telescope data, so imaging and spectroscopy of the source. We figured out that it's probably really far away, and that was still in 2022 in the fall winter. So, you know, within the first, let's say, 6 months of detection, which kind of, because we thought it was really far away and the image of the galaxy was really smudgy, as Emmy was kind of showing you, that tends to happen. So Alexa submitted this proposal to get telescope time on Hubble, which she got over this past summer, and then has been reducing it kind of this fall and doing all of the analysis, along with some kind of supporting observations at Keck and stuff like that.
So she was able to see it again.
Not the radio burst itself. So when I'm talking about these multiple periods of observation, these are all follow-up in mostly optical telescopes or near optical of the galaxy itself. So the fast radio burst, this one has only occurred just once in June 2022.
Thank you.
Mhm.
Great. Good
Yes,
job.
thank you. Okay, Rich also in the room.
You mentioned that the magnetars were spinning at a fast rate.
Mhm.
Do you mean that it's physically spinning, or that the pole, like it's a pole reversal that's spinning?
Yeah, so this question repeated for Zoom is a clarification of how magnetars spin, if I mean they're physically spinning or if the poles are processing or something like that. So when I say that they spin quickly, I do actually mean the entire star literally is spinning, like the Earth on its axis. The magnetic poles do also precess because these objects are just so extreme, but they precess. So they like aren't, so our magnetic pole is relatively stable, right? We like our compass north.
That's reversed in geologic.
Right.
And I'm wondering if that might be like, I'm wondering if anybody's studying that, like the fact that maybe it's pole reversal in the magnetar.
Well, I was thinking when you do two magnets together, you get that weird sound.
For Zoom, we're having discussion of magnets here.
And what is that sound? I've always just, you know.
Yeah.
When you try to push them together, you get that like yeah, it's like a swish or a,
The magnetic tension, yeah.
Yeah, sure. I can. So to maybe first for the poles, there's a lot of theories. We actually think that probably fast radio bursts are something occurring like out in the magnetosphere of the star. And there's some sort of like basically particle shower type process that's like really extreme. I don't think it's actually caused by anything physically with the presence of the magnetic field, like intrinsically. There has to be something to kind of kickstart this burst that's so rapid, like outside of like literally the magnetic process inside the star itself. As far as how magnets work, this is kind of gets into like so we don't have magnetic monopoles. You can't have like just the North Pole part of a magnet without the South Pole part. And so there are actually incredibly strong forces. Gravity is a really weak force. Like if you think how strong you think gravity is holding us all on Earth, the electromagnetic force is way stronger than that, like a lot of factors stronger. And so that's what you're feeling when you try and push a magnet together. So all of this probably plays into the production mechanism of a fast radio burst kind of in the magnetosphere, but we're kind of searching for something to kickstart that process. And that part is very unclear right now, I would say. I
I have a question online.
Okay.
How is a magnetar different from a white dwarf?
Yeah, for sure. So white dwarfs are not as dense as neutron stars. So white dwarfs are what happen when more average stars die. It's a less violent process and they don't collapse in quite as much. So a white dwarf star is much larger across, like several times the size of a neutron star. And they're still quite extreme environments, but there's just not as much pressure. A neutron star is a much larger star that has died in a much more violent process. It has a lot more mass, and all of that mass is squished down into a much smaller space. Does that answer your question?
I hope it does for Kate.
Thank you.
I would ask as a follow-up to that, how are magnetars and pulsars different, or are they similar?
Right, yes, good question. So magnetars are a special class of neutron star. Pulsars strictly are also a special class of neutron star, though it's possible that all neutron stars are pulsars. We haven't really sorted that out yet. So pulsars are neutron stars where the axis of rotation and the magnetic pole are misaligned, and they kind of sweep around like a lighthouse. This is a very quick and dirty explanation. Magnetars are they're the same kind of basic setup. You probably could have this sweeping effect on a magnetar. But what really makes the difference is that the magnetic field is many, many times stronger. So the environment is just that much more extreme than in your like kind of more run-of-the-mill, shall we say, pulsar or neutron star.
Thank you.
And Jack in the room?
Yeah, I guess I haven't quite formed my question in my head yet, but okay, so from my understanding, like to get like the image you have here with all the stars and galaxies and stuff, like you need that's like a really long exposure like time to like get all of that information. And I was wondering, like, are there other phenomena that are like really quick, like fast radio bursts, and like did we have to like completely redesign like telescopes or like the technology to be able to detect like the information in like a fraction of a second?
Real quick, that magnetar image was an artist's impression.
I'm just saying like in general, like
Just throwing that out there.
Yeah, no, that's a good question. So there is kind of a subfield, shall we say, of astronomy called transient astronomy, which basically deals only with very rapid events. So like supernovae, anything that like explodes or is like very short-lived. So there is like kind of a subsection of astronomy that was focusing on stuff like that. The other kind of piece that I'll say is radio telescopes work a bit differently. They are still sampled, but the data collection method is a bit different from that of optical telescopes. So the way that they kind of collect their data is rather different, and these signals are quite strong. So that's why we're able to pick them up in such like a short period of time, basically. Radio telescopes have like a lot less spatial resolution. That's why this picture, oh man, all the way back here of Jupiter is like kind of a lot like less detailed, shall we say, than the other images. And so just sort of the process of how long you're exposing and what you're actually getting with radio astronomy is a little bit different, which is an achievement, I would say, if that's helpful for fast radio bursts. But certainly still there was a lot that went into getting that localization and stuff. We did do a lot of redesigning our kind of analysis methods and the way that we read the data off of the telescopes in order to optimize for this case.
And also, as you go to arrays of radio telescopes, you get better resolution. So you're right, single dishes are not very, they're kind of like, it's over there in the sky.
Yeah.
What the real revolution for localization is building big arrays, which basically means building a much bigger radio telescope. Gives you better resolution, so you can pinpoint where they are.
And August, will you just restate the gist of the question that Jack asked?
Sorry. This question was basically telescopes in a lot of these science images that I've been showing you of those fields of galaxies have quite a long exposure time. And so how does that kind of build into these really quick signals of fast radio bursts? How does that kind of detection method work, basically?
Thank you. Another question at home. John asks, are all of your FRBs ones that are repeating? I imagine that that's necessary to be able to learn their position so well.
Good question, thank you. So actually the majority of fast radio bursts are just once-offs. We get one flash, that's it. There are a number of, it's a growing population, but still not a majority by any means of repeating FRBs. It's still technically possible because we haven't seen a ton of them yet that all FRBs repeat, but if so, most of them, like, it's a really long time between like repetitions. And so basically how we're able to localize FRBs so well based on a single burst is, as Regina was saying, using these telescope arrays. So these you're seeing kind of in the upper right, these are all like, especially these three are like single dish radio telescopes. So it's like one telescope. And these have pretty poor localization. That's kind of what I was talking about at the beginning. When we have these radio telescope arrays that we kind of put all of the data from each telescope together to make a giant telescope, we also have the information of like the like spatial spread information that allows us to localize to a much narrower area. And so even though we have just a tiny amount of time, when you have 100, say, radio telescopes all working together in tandem, that's really what gives us kind of the incredible localization power that we really need.
And to piggyback on that, how is it, apart from localization, how is it exactly, do you know that the singles and the repeaters have no overlap?
Can you define have no overlap?
In terms of that they are truly unique and not the same source.
Right, okay. So I guess the short answer to that is that we can't yet. That's kind of a big question. We have some like differences, like it kind of is indicative in a lot of the science that we're doing on FRBs that they don't necessarily like overlap in terms of their properties, like where they come from or what the pulses look like. But we really like can't definitively say that they're two populations yet. They could all be produced the exact same way.
Mm-hmm. Thank you.
Yep.
Celia asks, or rather says at the beginning, thank you for an excellent talk. Your explanation of the dispersion measure was so clear. For the FRB host galaxy that you're studying, have you found anything or any unique properties rather that shed light on what the FRB progenitor may be?
That's a good question. No smoking gun yet, unfortunately. Aside from the one local, like Milky Way FRB that was basically how that worked is it came from the same direction as a galactic magnetar that we already knew about, which was a pretty big clue that there's already something funky in that direction. And a lot of the theorists kind of hopped on the train of figuring out mathematically how that would work out. That's sort of how we developed the magnetar theory. There are some other things that you can do, like trying to determine the age of the galaxy to see if you would really expect a lot of stars to already be dead, right? If you have a really young galaxy, there are not necessarily going to be a lot of these magnetars, neutron stars, because they just really won't have had time to for the stars to live that long and die and produce these signals. But I've not in my work yet found anything that's particularly, shall we say, impactful on that question.
Thank you. Question for you. What, in your opinion, is the most urgent observational priority in FRB science?
That's a good question. There's a lot of things going on. I personally, I think, am partial towards the pushing boundaries where we have to get information deeper into the infrared in order to see further and further away. And so that's something that I personally am working on here at the Mariah Mitchell Association, is really trying to push that envelope about distance. That said, some people are really trying to prioritize radio telescopes that can see more FRBs. They say we get a bigger sample, we can learn more about them just because we have more numbers of detections, right? So it's a great question. In short, that's, I would say, looking further away, getting more deep data.
Thank you, August. And to round up, last question that I have from Dawn. Have any FRBs been located in an area that cannot be linked to a galactic area?
Yes, there are FRBs that have no successful localizations. We're trying our best to solve those problems. We don't necessarily think that we have wandering FRBs that were produced just out in the visible space. Most likely it's because the galaxy is just too faint for us to be able to detect it. But it's a good question, and it is certainly, there's a non-negligible sample of those where we don't actually have an answer of, yes, this came from this galaxy.
And what are you most excited about for your trip to Keck?
I would say, yeah, it's a good question. I'm really excited to get data, particularly that is impacting my specific science, right? Like spectra, that it's putting the two pieces together for me. I've, throughout the process of this research, been doing a lot of analysis of spectra from the Keck telescope and from others. And so being able to see that data literally from collection all the way through to processing and science results is going to be really exciting, I think, for me.
Amazing. Well, good luck to you both on your upcoming trip to both Keck and to the AAS.
We have
Yep.
another question.
Sorry,
in the
yeah.
room. Yeah, go ahead.
Go
Jen.
for it.
So when I was a kid and we looked up at empty space, and it turns out it's so not empty.
Right.
So back in time, and you're looking through more layers of stuff, how does that influence the spectra? Does it change them? It's just by travel, like does things fall apart or collide or?
Do you want to repeat the question?
Yeah, I can. So Ginger started with an anecdote that we used to look up into empty space that's not so empty, which I really appreciate. And then the question is basically how does all of the like kind of material and looking further and further away actually impact what we're observing, right? It's as we kind of branch out to these deeper objects. So I guess I'll take this opportunity to utilize a couple of my bonus slides. The first is that indeed, like in reality, the picture is a lot more like this. Like there is a lot that we have to account for on all of our lines of sight, especially the further we're looking away. And so it's kind of a pretty big scientific undertaking, basically, to map out all of this stuff that signals are going through, and they do all impact the signal that you're seeing. And so that's a very big piece of it. And also using different wavelengths of light helps us in different ways to do this. So some wavelengths are a lot better at seeing through clouds of gas and dust than others. This is kind of tricks in observational astronomy. I don't actually have it here, but you can look up like the multi-wavelength universe and you'll see just a picture of our Milky Way, and some wavelengths of light really get like stopped by foreground clouds of gas and dust, and some of them pierce really well and we can see way farther, way clearer. So there's a lot that goes into doing that for sure. And there are some other complications that are summarized basically here. I'm not going to get into what all this means unless you ask me, but it basically means that the wavelength that light was emitted from is not the same when it gets to us, and this gets worse the further away we look. And sometimes that can be an advantage and sometimes that can be a disadvantage, just depending on like if these overlap with some other emission line and we just like totally lose our data, right? Like if there's something emitting right here, like in our atmosphere, this is something I have to deal with, right? Like we totally lose this line because it's like obscured by the blue of the sky, shall we say. So it is a very complex problem in short. Yeah.
Cool.
Thank you. Did you have one more question? Okay.
But I think spectroscopy, to tie it full circle, spectroscopy helps answer exactly those questions. Because if you just take a picture, visually, we're only seeing one side of the story. But if you break that into spectra, you can see much more detailed picture. And then if you go to other wavelengths as well, radio and whatnot. So you really kind of need to do the whole thing to understand fully. Any more questions in the room?
One more comment from at home. Dan Bursch says, again, applause, applause. Thank you so much, Regina, August, and Emmy. Good luck with your trip to Keck. Hope for clear skies, no volcanic eruptions, no snow, no high wind.
Thank you, Dan. All right. Cheers.
Cool. Thank you so much. Yeah. Good job.
Thank you again, August and Emmy, as well as Regina, and to everyone for joining us this evening. Thank you so much from the Murray Mitchell Association. On behalf of Bank of America, Cisco Brewers of Nantucket, and the White Elephant Hotels and Resorts of Nantucket and Palm Beach, we would like to just say thank you again for making this information accessible to everyone, as well as to sharing what work you are working on currently and your upcoming research. So again, thank you, everyone. I'm Janelle Gurley. Have a great evening.